You may start whenever you're ready.
Okay. So can everyone see my screen or hear me clearly?
Yeah.
Okay, thank you. Okay, so hello everyone, I'm Sijia. I'm a 5th year PhD student from the University of Michigan working with Professor Ian Hiskens. I'm glad to present our work on chance-constrained optimal capacity design for renewable-only islanded microgrid. The talk will break into 5 parts. Firstly, I will give some background of this work. Then the problem description and microgrid model is provided. The optimal capacity design problem will be formulated into a chance-constraint optimization problem. We then propose 2 novel robust set formulation methods based on the cutting-based method and principal component analysis. Finally, the test results and discussions are given. The rapid depletion of fossil fuel and the increasing concern on environmental issues demand renewable energy resources such as wind and solar, which have been proved to be eco-friendly and cost-efficient. However, integration of large amount of renewable resources is challenging because the power output from wind and solar is uncertain and intermittent. Microgrids provide the opportunity to incorporate more renewables. Microgrid is a small-scale power system that groups a variety of distributed energy resources, especially renewables, together with energy storage and loads to provide better control and operation. Microgrid can operate off-grid as a standalone system. Furthermore, we consider the case with no backup generator to investigate the renewable-only setting. In this case, the battery is a necessary component to shift energy generation. Also, load shedding scheme is allowed in the case of limited renewable generation. The objective of this work is to optimally design the capacities of distributed energy resources in an islanded microgrid so that energy sufficiency is guaranteed and the design cost is minimized. The design process we propose can be extended to an energy hub setting with multiple energy carriers, which is addressed in our follow-up journal paper. The main challenge we have is to deal with the stochasticity in renewable resources and load. The microgrid we considered is composed of renewable generation units, including wind turbine, solar PV, a battery energy storage system, and controllable load. Among these components, the wind turbine, solar PV, and load are modeled as stochastic units, which will be represented by time domain trajectories. The battery system is modeled as a deterministic first-order state of charge model. And the economic models of DERs is captured by the net present cost, which computes the life cycle cost of the microgrid. The capacity design problem is formulated as a chance-constraint optimization problem of the form P0, where the constraint 1 is the chance constraint. Due to the existence of stochastic variables, instead of enforcing hard constraint, we only require the constraints to be satisfied with high probability so as to render a less conservative design. Here, delta are the random variables. In our case, they are the random power generation from renewable units and the load. And X are the decision variables that are the component capacities. And epsilon is a pre-specified validation level. So chance-constraint problem is in general very hard to solve. To render it tractable, control policies are designed to generate trajectories for battery charging, discharging, and load shedding under arbitrary generation and load conditions. To assist the design of FM policy for battery dispatch, we first assume a nominal trajectory for wind, solar, and load power. We search for the nominal battery dispatch trajectory and the policy parameters. The FM policy is of the form of equation 2, where constraint 3 is to enforce that battery state of charge at the end of the horizon return to its specified initial value. The load shedding ratio R denotes the proportion of load that must be shed at any time t. The load shedding policy is given by equation 4. Note that this load shedding policy is not explicitly included in the optimization problem, but rather enters implicitly through power sufficiency requirements. The capacity design problem is summarized as in problem P1. P1 designs the capacities for DRs and load shedding to guarantee energy sufficiency with a priori probability guarantee while minimizing the net present cost. The objective function consists of net present cost of all components together with the penalty on load shedding limit. We enforce a chance constraint for power sufficiency, battery power limit, and battery energy limit. The constraints for FM policy is included, and a set of deterministic constraints need to be enforced for the nominal trajectory. Finally, non-negativity constraints are included. To solve the problem, a standard scenario-based approach, as in reference 1, can be used. However, scenario approach approximates the stochastic constraint by a set of scenarios, each of which is a realization of the random variables. Although scenario approach can solve P1 with probability guarantee, it requires a large number of scenarios, and this leads to a heavy computational burden. Moreover, a large data set with decades of records is hardly available. We can instead use robust counterpart approach. This approach firstly constructs a chance constraint problem P2 to search for a hyperrectangle robust set for the uncertain variable. Next, a robust counterpart of the original problem P1 is solved with uncertain variables constrained to the robust set. This way, the computation requirement can be reduced significantly. However, this method may be conservative. The hyperrectangle robust set, as proposed in reference 2, will lead to a conservative result if the random vector has high dimension or large variance. In the following, I will present 2 novel methods to improve the robust set formulation. They are the cutting-based approach and the PCA-based approach. The first one is a cutting-based approach. So the box-shaped robust set is conservative because it completely loses sight of the temporal relationship in stochastic renewable generations and load. As a result, the design has to cope with minimal availability of wind and solar resources over the entire horizon, which is a rare case in reality. We thereby propose a cutting-based approach to refine the hyperrectangle robust set so as to capture the temporal relationships and reduce the conservativeness. We introduce a hyperplane to cut out the unnecessary portion. So only one extra design variable is introduced in P2 that describes the distance of the hyperplane to the corner. Thus, we can achieve the same probability guarantee by only introducing a small number of extra scenarios. We further exploit principal component analysis to reshape the robust set. PCA analysis converts the data into a new set of coordinates, the principal components. These PCAs are arranged in a descending sense, such that the first PCAs capture most of the variations in the data. Under the guidance of PCA, we introduce 2 hyperplanes for each PC. These 2 hyperplanes are normal to the PCA direction, and their offset to the origin are determined by the 2 outermost data points in the PC direction. As illustrated by figure 1b, the intersection of the half space defined by these 4 hyperplanes give rise to a hyperrectangle, the light blue rectangle, in the PC space. Intersecting this set with the original robust set, the gray rectangle, gives us a smaller robust set that is a polytope with red boundary. The refined robust set still encompasses all the data points and is less conservative. This allows for more flexible control policy for battery dispatch. And as an implication of PCA, the last few PCs contain the least variance in the data, which suggests efficient cuts. With the proposed robust set, we can now reformulate chance constraint problem P1 into its robust counterpart, referred to as P3. Problem P3 is a robust linear program with polytopic and certain set, which can be transformed into a regular LP through taking the dual. By proposition 1 of reference 2, any feasible solution of P3 is an epsilon level feasible solution to P1 with probability at least 1 minus beta. The test results will be discussed in the following. In this work, we use true generation and load data from online database. The economic model parameters are summarized in table 1. For chance constraint specifications, we give a validation level epsilon of 0.1 and confidence parameter beta of 0.1%. The optimal design results are summarized in table 2. Compared to the benchmark box-shaped robust set, since the cutting-based method eliminates the critical small corner, conservativeness is reduced significantly, and therefore we see a cost reduction. The PCA-based approach, on the other hand, eliminates a large volume from the robust set. This may not directly affect the LP solution. However, it is able to render a more flexible FM policy. Therefore, the combined CAT and PCA approach leads to both lower cost and reduced load shedding rate. Due to the robust nature of our approach, scenarios that actually require load shedding are rare, and the amount of load shedding is small for most of them. For the combined method, among the entire about 2,400 scenarios, only 14% require some load shedding. Figure 2 shows a profile for the maximum load shedding for each of the scenarios, ordered from the highest amount to the lowest. The curve drops quickly and is 0 for most of the scenario. To demonstrate the FM policy for battery dispatch, we plot the state of charge dynamics for various cases in figure 3. The nominal forecast trajectory is shown as a purple line, and for other trajectories for various random scenarios are plotted as dashed lines. It is clear that the state of charge at the end of horizon is driven back to its initial value in all cases, and all trajectories respect the upper and lower state of charge constraints. The plot also shows 2 boundary cases that approach the upper and lower state of charge limits. The power profile of a case requiring load shedding is shown in figure 4. In this case, renewable generation is insufficient overnight to meet the load requirement. So the battery discharges at high power to compensate for the generation deficiency. However, load shedding is still required, and the maximum load shedding is about 27 kilowatts. This case also illustrates the necessity for high wind power capacity in the design of the purely renewable microgrid. In this case,
have 1 minute.
Okay, in this case, wind generation is low over most of the day, and solar generation is only available during the daytime. As a result, the wind turbine capacity needs to be sufficiently high to meet the demand. Finally, I'd like to provide some concluding remarks of this work. We consider the problem of optimal capacity design for DERs in a renewable-only islanded microgrid. To address the stochasticity, we formulated the problem as a chance-constraint optimization problem. An FM policy for dispatching battery power is proposed and integrated into the optimization formulation. We propose 2 methods, the accounting-based approach and the PCA-based approach for reducing the conservativeness of robust reformulation. Thank you very much for your attention. If you have any further questions, please send us email or ask now. Thank you.
Okay, thank you, Sijia. I'm waiting for a couple of questions.
Okay.
Until I see some, yes, here they are. Okay, so from Nawaf Najir, how can you make sure there are no breaks or holes in the feasible space of the obtained capacities.
Sorry, could you repeat? There are no
breaks or holes in the feasible space of the obtained capacities.
Of the obtained capacities? Do you mean the feasible space of the chance constraint problem?
I would think so.
Okay. Sorry, I don't get the question very well. So why do I need to make sure there's no holes?
So, okay. It's a little bit a tricky question. I guess maybe he can rephrase it and put it aside again. I don't really get totally the point as well.
Okay.
Let me see the next one from Jonathan Dumas. Okay. What about green performance key indicators to be taken into account for the sizing, such as self-consumption, carbon footprint, raw material requirements, etc.? Would you like me to repeat?
Yes, actually, I'm looking at the Q&A.
Okay. Okay, that's good.
Is the question from
Jonathan Dumas, the last one? So he's asking whether you could include key indicators in the sizing problem, such as consumption, carbon footprint, raw material requirements.
Oh, I see. So we can formulate that in the objective function, but currently my objective function is a linear function of the decision variables to make the overall problem formulation to be a linear problem. So in that case, if everything can be formulated as a linear function of the capacities, which is the decision variables of the DRs, then yeah, we can formulate that.
Okay. So let me check. There is another one. Okay, there's no other one. Maybe I have one. So I'm wondering if you can give some insights of in what kind of distributions of the uncertainty the proposed methods that you showed here for reducing the conservativeness of robust reformulation, these benefits will be more highlighted.
I see. So firstly, since we are using the scenario decision approach, we do not assume the underlying distributions, and it is actually an advantage of the scenario approach. And for the proposed, for the method I proposed, the robust set reformulation approach. So if the distribution gives you more higher probability for outliers, then, for example, the cutting-based approach can cut out the unnecessary portions of the random variable. So in that case, it will benefit the decision. It will benefit the LP solutions. But for the PCA solution approach, it considers more about the distribution along the PC directions. So that means if there's a more biased distribution along the PC direction, then I can cut off the more volumes from the robust set for the rest of the PCs. And in that case, we can get a more flexible FM policies for the battery dispatch. So that's basically my insights for this question.
Okay, thank you very much, Sijia. Great talk. We should continue to the next one now. It's time.